Welcome for today's lesson. I'm going to take you through a lesson for today. We're going to look at uniform circular motion. My name's Siamasaka, clear and dense. Here we go. Okay. As I said earlier, today we will discuss uniform circular motion. You know, all objects, those that are moving around a cycle, actually experience uniform circular motion. So, uniform circular motion is the motion of an object traveling at constant speed around a circular path. And so, even if it has a constant speed, there is acceleration because at every point there is a change in the direction for the velocity vector. And so, we also need to understand what the period is. The period for actually this movement is actually the time required to travel once around the circle or one revolution. And so we have defined what actually the period is. And so the velocity, we would say it's actually the distance over time. So if it's moving around the circle, we would say it is the circumference distance divided by time. And the circumference is given by 2 pi r. Okay, so velocity therefore is equal to 2 pi r over t, and t is the period, that's the time for one revolution. And so centripetal acceleration is actually an acceleration vector that points towards the center of the circle. And so an object which is moving around the circle experiences some acceleration, and its vector acceleration points actually towards the circle. So for very large radius, acceleration becomes zero because actually velocity becomes constant. Because actually, if the radius is very, very, very large, it means that actually what it entails that it is going towards actually zero. And so acceleration becomes zero because there will be constant velocity. An object in uniform circular motion can never be in equilibrium. What this means is that since there is always acceleration, it means that there is no way an object can attain equilibrium state. Because earlier we indicated that an object, for it to attain the equilibrium state, it means that it should not be accelerating. And so now we are going to derive centripetal acceleration. Imagine there is a circle and it has a center at A. It has the radius, which is AC, and the AB. And then here it has a chord, which is actually the difference of the two, which is R, delta R. And then we have a tangential at B, we have a tangential velocity V1, and another tangential velocity at C, which is V2. And then here we have a sector, which is delta S. And so if we are to draw this velocity, so we're going to have velocity 2 and the velocity 1, and then the difference between these two would be delta V. So we have this triangle PQR. And so as I indicated, delta V is equal to V2 minus V1. Okay, and so we note that actually ACB because of the angle theta, which is very small here, it can actually be a similar triangle to PQR. And so you notice that actually what we are saying is V1 is equal to V2, which is equal to V. So the velocity, tangential velocity here can be stated as to be equal to, because the length is the same, V1, V2, and which gives us actually the velocity. And so, as I indicated, we note that actually delta V over V, since we said actually delta V over V is equal to delta S, which is actually the displacement for this point here. So the displacement over R, which is this radius. These are similar triangles, so you can actually say this delta, because this is very small, delta S over R, and here you can solve delta actually V over V, because we said V2 is equal to V1. Okay, so we can make delta V, which is the velocity, the subject of the formula, and it will give us actually velocity over the radius multiplied by the delta displacement. Okay, the difference in displacement. And so we can divide this equation here, we can divide both sides by actually changing time. So the change in time here and here, we can divide also by the change in time. So we have divided here by change in time and here also by the change in time. So what we get here, change in time, and here we divide by change in time. You know, the change in velocity over change in time is actually acceleration. So if we, again here we said the change, which is change in displacement over change in time, which is actually velocity, meaning that V multiplied by V would give us V squared, okay, and then over R. And it means that actually we have verified that acceleration, which is pointing to the center of the circle, which is centripetal acceleration, is equal to velocity squared over R. So this is actually a very simple process of proving that we can derive actually the acceleration from a circle. Okay. And so centripetal acceleration is acceleration as we defined it, is acceleration which is pointing towards the center, which is gotten by the velocity squared over the radius of that curve or circle. So now we look at centripetal force, which is actually the net force which is required to keep an object on the circular path. It also points towards the center of the circle. As you know, we said that acceleration is equal to velocity squared over R. And you know from Newton's law of second of motion, we stated that force is equal to mass times acceleration. So actually here we are multiplying just mass multiplied by centripetal acceleration, which actually gives us velocity squared over R multiplied by mass. Very simple, and therefore this gives us now centripetal force is equal to mass velocity squared over R. So I thought this would have given us some concepts of understanding centripetal acceleration as well as the centripetal force. And so we go now straight to look at a simple question which will enable us actually to cement our understanding of these concepts. The first equation reads as follows. Calculate the centripetal force exerted on a 1,500 kg vehicle that negotiates a 300 meter radius curve. Also note that the vehicle has a speed of 50 meters per second as it negotiates the curve. If the vehicle is not to slip as it moves on a banked load, find the minimum static coefficient friction between the tires and the load. And so the solution will go as follows. So it's a simple version of application of actually centripetal force. We stated that centripetal force is equal to mass multiplied by velocity squared over the radius. And therefore, we just substitute. We said the mass is 1,500 kg multiplied by the velocity, which is 50 meters per second times 50 meters per second, then over the radius, which is 300 meters. And we get 12,500 newtons. So as simple as that. And so the second part of the equation is asking us to find it is stating that if the vehicle is not to slip as it moves on the unbanked load, find the minimum static coefficient of friction between the tires and the load. And we note that actually the centripetal force is equal to coefficient of static friction, because this is the actual friction which will enable the vehicle not to slip, multiplied by the normal force. And the normal force, since it's tangential to this mass, actually it is equal to mass times gravitational acceleration, which is mg, which should be equal to actually the value for centripetal force, which is mass multiplied by the velocity squared over time. And so we are to calculate here the coefficient of static friction. We just make this one the subject of the formula. And we note that if we made this one the subject of the formula, the mass here, mass there, they will cancel. So I want to remain with the velocity squared over the radius multiplied by gravitational acceleration. And therefore, may I substitute 50 meters per second multiplied by 50 meters per second over the radius, which was 300 meters multiplied by acceleration due to gravity, which is taken as 9.8 meters per square seconds. And this gives us 0.85. Actually, it has no units. So the coefficient of static friction is actually 0.85. So this one has helped us that actually this is a very high coefficient of static friction, which will enable the vehicle to remain gripped to the ground without sliding. So at times we can be asked to find the maximum speed around a curve. So you notice that here we have a vehicle which is negotiating a curve. So it has the velocity which is tangential to this curve, which is the circle, and therefore it will produce a force towards the center, which is known as the centripetal force. And so the maximum speed around a curve, then it would be actually the centripetal force, which is equal to coefficient of static friction multiplied by the normal force. So this would be the force which would be also directed towards the center, which will enable to resist the actually sliding of the vehicle, as we indicated the area, multiplied by mg, which is equal to mass times velocity squared over the radius. And so you notice that here, actually the mass can go, this mass and that mass can cancel, and we're going to remain with the coefficient of static friction multiplied by acceleration due to gravity, which is equal to velocity squared over the radius. If we are to make the velocity the subject of formula, This is what we get, which is squared g r mu. Okay, so we note that actually the velocity of the object or the vehicle, which is negotiating a curve, does not depend on the mass. So a very big vehicle like a lorry or very big vehicle and a small vehicle, what would depend on actually on them to negotiate actually a curve is merely its speed and not the mass. Okay, this is a very important concept that we need to know. And so at times, to avoid the stripping of these vehicles when they are negotiating a curve, we find that the road is actually banked. Banking means, when they say banking curves, which means that the road is made to slant. And therefore, we are making here the vehicle. We assume that there is a vehicle here, and this is the angle, and this is the horizontal, so that when it is negotiating when it's negotiating a curve, the vehicle will not be actually flat, and therefore much of its force will be actually towards the center of that curve, so that it does not strip away off the road. And so we see that if this angle of slanting is actually theta, it means that this angle also be theta, meaning that if we drew the normal, which is always perpendicular to the plane of the slant, okay, then it means that the prolonged, the one which goes through the weight would be actually, if we are to resolve this in two components, we're going to have a normal multiplied by cos theta, because this angle is actually adjacent. And then the opposite one there to be the normal force multiplied by sine theta. And we notice that this normal force sine theta is actually parallel to this force, which is centripetal force, which is towards the center. And therefore we can say the centripetal force is equal to the normal force multiplied by sine theta, because these are actually parallel. This is a very important concept because just the equating of the force to actual normal force times sine theta is a very important concept, because if we cannot do that, we cannot actually rise. It means that we cannot actually proceed. And we note that also this distance from where the vehicle is to the center where of the curve here this is the radius. Okay. And so we note that as indicated earlier on here, we said the centripetal force is equal to the normal force multiplied by sine theta, as we indicated here, which is the same as this one, which is equal to mass times velocity squared over r, which is actually the centripetal force. And therefore, from here, we can actually know that again, if you check here, we said this weight is equal to the component of the normal force, which is the normal force cos theta. And this is what we have written here. mg, which is the weight, would be equal to the normal force cos theta. And so, if we are to divide these two equations, you divide this one, the normal force. Why are we doing this? Because we want to eliminate the normal force. The normal force sine theta over the normal force cos theta, which should be equal to mv squared over r divided by mg. And this is actually what we have done here. And meaning that the normal force here will cancel, would remain with the sine theta over cos theta. And from trigonometric identities, we know that sine theta over cos theta is equal to tan theta. And if we simplify this one, it means that the mass actually will disappear. We are going to remain tan theta is equal to velocity squared over the radius multiplied by acceleration due to gravity. So this is a very big, important concept that on a banked curve, as we indicated earlier, the mass of the object which is actually negotiating a curve does not come into play. Okay, what matters is actually its velocity and the radius of the curve. So, we can say that greater speeds and smaller radii require steep banked curves. What it means that if the speed is very high here, it means that we require an angle which is large. Okay, therefore it will be steeper. Or if the radius is very small, it means that equally we require a very steep banked curve, meaning that the angle should increase. So we have another question here, which we thought would go through again, so that we can cement what the concepts that we have learned so far. So the question goes as follows. A curve of radius 100 meters is banked at an angle of 15 degrees. At what speed can it be negotiated if there is no friction involved? So this is actually the equation that we derived here. Okay, and so we are saying tan theta is equal to velocity squared over r, the radius over acceleration due to gravity. So we can make V the subject of the formula and then substitute the radius. We said it was actually 100 meters, and then multiplied by G, which is 9.8, multiplied by tan 15, which is actually the angle. And what we get here, it is actually, the rest we get is 16.2 meters per square seconds. So the speed is actually dependent mainly on the radius and the angle. And therefore, I thought today we can look at these few concepts on actually centripetal force, centripetal acceleration, basically also on centripetal uniform actually circular motion. And so I thought this would be of benefit as we go to actually look at more difficult problems. And therefore I end the lesson for today, but remember to subscribe to my YouTube so that you can continue getting these interesting lessons. I thank you.